So let V be an affine variety with the coordinate ring, this K of V, and let M be a KV module. And let this curly U be the cover of this V. So these UIs, they completely cover our affine variety V, and this cover is finite. So these UI are finite open sets. So we have a finite open cover of V by the standard affine sets. So finite means you just choose a finite number of them. So 1, 2, 3 all the way to M. So now we put a quasi-coherent sheaf on our variety V. So for quasi-coherent sheaf V, we choose this module M. So for f of u, you will have M tilde. So then for all p greater than 0, this HP, the cohomology groups which we will compute from check complex, they will be 0. So this check at the top denotes that this is the cohomology computed from the check complex. So you can find the proof of this result on page 118, Algebraic Geometry by Daniel Perrin. And you must read the proof after going through this lecture. So first recall that how is this UI cut out. So UI is cut out by some polynomial fi not equal to 0. So you have your variety V like this, and then you have some polynomial this fi equals to 0. So this cuts it at 2 points. So if you delete these 2 points, the polynomial is not 0 on the rest of the set. So taking these 2 points out, you have fi is not equal to 0 on the rest of the set. So this is the set ui which is cut out by our polynomial fi not equal to 0. So we first handle the case for p equals to 1, and then we will generalize to everything else. So what we do is we take sets of the form uij, ui intersection uj. So because p is 1, so first index is 0 and second index is 1 according to the notation in Daniel Perrin's book. So first let us draw some diagrams and understand how this uij sits in the complex. So this uij is intersection of ui and uj. So this sits inside ui and it sits inside uj. So now when you apply your sheaf to it, there is contravariance. So this goes in like this. So take this element gamma I, which is a section of f of ui, and you have this order. So I is less than j. So this is 0 and say this is 1. So when you take in gamma I, j is missing. So when it sits here, you write it as gamma I j, j is missing. So j has index 1. So you multiply it with minus 1 to the power of 1. So this becomes minus gamma I. So minus gamma I because j is missing anyway. So this is gamma j. When it comes here, that means I is missing. So this gamma j becomes gamma I hat j. But this is in the 0 position. As you can see, 0 is here. So minus 1 to the power of 0. So this is just gamma j positive. So you get this. So two elements, gamma I and gamma j, they will get mapped like this, gamma j minus gamma I. So now we should also see what are the sets which are sitting inside uij. So any set sitting inside uij is of the form uijk. So it's of one index higher. So this is in the higher complex. This is in C2. And our convention is 0, 1, 2. So now we already have set I is less than j. Now you set k here. So now you have 0, 1 and 2. So this uijk sits inside uij, but this also sits inside ujk, and it also sits inside uik. You apply your sheaf f to it, you have contravariance, so arrows are going in the opposite direction. So now notice the section alpha ij in this sheaf fuij on this set. So this section, this gets mapped right here. So to map it right here, you just write again alpha ij, but k is missing. So you put a hat on k, and notice that the index of k is 2. So you have minus 1 to the power of 2. So this becomes plus alpha ij. K is missing anyway. So this is plus alpha ij. So now consider this element alpha jk. So this will get mapped here. So alpha jk, it is still alpha jk, I is missing, but you see I is in the 0 position, so you have minus 1 to the power of 0. So again this is positive, this is positive. So now we have alpha ik, so this alpha ik has j missing, so j is missing, so it gets mapped here, but j has index 1, so minus 1 to the power of 1. So that's what you get here, you get minus alpha ik. So we have accounted for all three elements. So we want to show that these check cohomology groups are 0. So recall the definition of check cohomology groups. So this is nothing but kernel over image. So kernels we call as cocycles. So we want to say it, if alpha ij is a cocycle, then it comes from a co-boundary. So this co-boundary is image of something. So this alpha ij, this sits in C1. So this sits in our C1 going into C2. So our map, this cohomology group is kernel of this map. So this is equal to 0. So this is the kernel of the map. So we are saying this alpha ij sits in here, and this relationship is forced to us because you have to consider uijk sitting inside uij with the indices. This is in C2, the C2 here, so this sits inside here, so this is forced. So this is our kernel part. So we are saying this alpha ij, if it is part of cocycle, that if it satisfies this relationship like this, then it comes from something like this, gamma j minus gamma I. So this is equal to this. So after all, this is section here in fuij, this is also section here in fuij, but this is now coming from this C0. So this image is coming from C0. So we are talking about just 1, p equals to 1. So if we show this, then we are done, and that's what we are writing here. Alpha ij is equal to gamma j minus gamma I. So this we have to show. Then obviously the cohomology groups would be 0 for p equals to 1. So this alpha ij is now you can write as minus alpha jk plus alpha ik. So basically rearranging this, you have alpha ij here and take the other two terms on the other side. So what does this alpha jk come from? This alpha jk obviously sits in this set. So this is cut by fj and fk. So you have in the denominator you have fjn, fkn, and the numerator is just an element of module. Similarly, alpha ik, it sits right here, so it is cut by fin and fkn, and the numerator just sits in the module. Now what we want to do is we want to transfer this alpha ij to sets uj and ui, and uj is cut by fj and ui is cut by fi, so it makes sense to transfer this to this side. So let us do this. You multiply both sides by fkn, this is also multiplied by fkn, and then this fkn is not in the denominator here. So we almost want to put this as, say, negative gamma j, and this is gamma I. So if we put as negative gamma j, you could get gamma j minus gamma I. So we almost are done, but we want to get rid of this fkn. So if we want to get rid of this fkn, we have to use a trick. So the trick comes from Nullstellensatz. So you know 1 is equal to k equals to 0 to m, where m is your total number of sets which are covering. Each set is cut out by one of these fi's. So you ak fkn. So now you put alpha ij, multiply on both sides, you get alpha ij fkn. So now instead of alpha ij fkn, you just plug in this. So you plug in this value, and now you're almost done. So now you can set gamma j as negative summa ak mjk by fnj. So you're setting it negative because gamma j is positive here. You can't get rid of this negative sign, and then this positive will become negative. So instead of gamma j, you put gamma I here and fi here and I here, then you get gamma I, and that's pretty much it. So you just set this gamma j as this because this function lives on set uj. So you put it like this and you get gamma j minus gamma I. So we have been able to show that this alpha ij on one side, just using Nullstellensatz, will give you gamma j minus gamma I, precisely because this function lives on j and this function lives on ui. So fj is cut out set uj and fi is cut out set ui. So that's why you can put gamma j and gamma I. Now the same idea carries over to higher p's. So because now you will take alpha from I0, I1, IP. Now you have the numerator which is part of the module, but the denominator is cut out by these sets fi0, I1, IP, and precisely in this case it was cut by jk. Here it is cut by all these things here. And for gamma, since you're again going to use null cell and sarts, you just need to get rid of one of the elements here, which will generate 1. So you just get rid of one of them. So that's why we're writing p minus 1. So basically you will get rid of this term in the end. So this will give you ak and this, and then you just do the same thing. Same ideas will carry further. So now you will have here you just had two I and j's because your set was uij you were dealing with, but now you are dealing with ui0, I1 all the way to IP. So there are a lot more gammas here, but essential idea is precisely the same. So you still use null cell and sarts, you have a single value corresponding to this IP, and then you proceed exactly the same, just set appropriate gammas in the end. So there is an important corollary to our theorem. So our corollary says that, say you have V, which is an affine algebraic variety, and on that you have exact sequence of quasi-coherent sheaves. So you have 0, F, G, H. So that would imply that you have exactness of global sections also. So the global sections are exact. So in general, these global sections are not exact because starting here, you start putting in H1 and H1 of V F, then H1 of VG, H1 of VH. You keep on going, putting cohomology groups here, but we are saying all these cohomology groups are 0 for p greater than 0. So you have exactness of global sections.